Welcome back to the deep dive. Our mission today, well, it's all about lifting the hood on large language model fine-tuning. We're going to move past the basics of LoRA and get straight into the stability toolkit.
Yeah, those like 4 advanced levers. The ones that really dictate whether your specialized model can even train on the hardware you've got.
Exactly, because fine-tuning, it's amazing, right? It takes a generalist model, something like Llama or Gemma, and sharpens it for your specific needs.
It really does. But it's always fundamentally a high-wire balancing act. You're juggling quality, speed, and fitting it all into that precious VRAM.
Oh, yeah. And if you've ever had a project just crash with that, that dreaded out-of-memory error, well, these levers are basically the difference between success and total project failure.
Absolutely critical.
So we're calling these the VRAM stability levers. We're focusing today on, let's see, mixed precision, batch size tuning, gradient checkpointing, and quantization.
And the good news is you don't actually need to be like a deep PyTorch expert to use them.
Yeah.
Mostly, you'll interact with these through higher-level frameworks. Think Hugging Face TRL, Axolotl.
Right, where you just flip a config flag, like setting BF16 true or something.
Exactly. But understanding what that flag is doing, that's how you go from just, copying recipes to actually optimizing your setup.
Okay, so where do we start?
Let's start with the absolute foundation. The one lever that pretty much made modern, large-scale LLM training even possible in the first place. Mixed precision.
Okay, mixed precision. Let's unpack this. We know neural nets are basically weights, numbers. Why did we always use 32-bit floating point FP32 traditionally? And why is that kind of obsolete now for these massive models?
Well, FP32 gave us maximum numerical accuracy. You can think of it as like the safest, highest resolution setting. But when you're dealing with models that have billions, literally billions of parameters, using 32 bits for every single one means 2 big problems. First, astronomical VRAM usage just eats memory. Second, it's slow. General hardware kind of struggles to process that sheer volume quickly.
Right. So mixed precision is the elegant compromise here. We cut the size of most numbers in half down to 16 bits for the bulk of the calculations.
Exactly. And that immediately roughly halves your VRAM usage, which is huge.
Huge. But it's not just about saving memory, is it? It's also about speed.
Precisely. By moving to 16-bit math, we unlock specialized hardware that's built into modern GPUs. NVIDIA's Tensor Cores, for example. They're specifically designed to just crunch through 16-bit operations much, much faster.
So you get faster training and halved memory use. It sounds like a win-win.
It pretty much is. It's basically non-negotiable for any serious fine-tuning today.
Okay, wait. If 16-bit is faster and saves memory, why is it mixed precision? Why not just do everything in 16-bit? Wouldn't the 32-bit parts just slow it back down?
That's a really good question. It really comes down to stability. There are certain very critical calculations, especially involving the gradients, those tiny updates we calculate during learning. They need the really wide dynamic range of FP32. If you use 16-bit for everything, some of those very small but important numbers can just round down to 0. It's called underflow.
And that crashes the training.
Yeah, it can totally derail the whole process. So the mixed part means we strategically keep those crucial sensitive operations in FP32 to maintain stability, while doing the vast majority of the heavy lifting in the faster, memory-saving 16-bit format.
I like the photo analogies before. FE32 is like this super high-res, raw image file, full color depth, everything. 16-bit is more like a high-quality JPEG.
Right.
It looks almost identical for practical purposes. The final model quality is usually indistinguishable, but the file size, the memory footprint, is cut in half. It's that trade-off.
Exactly. And when you actually enable 16-bit, you'll typically encounter one of 2 main formats. The modern gold standard, especially if you're on powerful GPUs like A100s or H100s, is bfloat16 or BF16.
BF16.
Yeah. It cleverly maintains a very wide dynamic range, similar to FP32, which makes it extremely stable. It's often just a drop-in replacement, works great.
But there's an older one too, FP16. Still see that around sometimes.
You do. FP16 actually offers higher precision, but within a much narrower numerical range. And that's the catch. With FP16, those critical gradient numbers we talked about, they can still sometimes underflow, go to 0. So if you're using FP16, you often need this extra technique called loss scaling.
Loss scaling. Sounds complicated.
It kind of is. You have to artificially inflate the loss value before calculating the gradients, then scale everything back down afterwards. It's extra overhead, more complexity.
The takeaway is pretty clear then.
Yeah, absolutely. If your hardware supports BF16, and most modern training GPUs do, you just set BF16. True. It's simpler, it's stable, pretty much end of story for most users.
Okay, perfect sense. So, mixed precision gets your LLM training actually running. Lever 1. Now let's talk about lever 2, the one that manages like the volume of work and throughput, batch size. And this clever trick with gradient accumulation.
Right. Batch size is just how many data examples you process at the same time. Intuitively, a larger batch is better.
Why is that?
Well, it keeps the GPU busy, more saturated. Better hardware utilization means better efficiency, faster throughput overall. Plus, larger batches tend to give you slightly smoother, more stable gradient updates during training.
Okay, but the big problem is VRAM, right? Try to use a large batch size.
And you hit the memory wall almost instantly. Especially with large models, it's often just impossible.
So this is where the clever hack comes in, combining micro batches with gradient accumulation, or GA.
Exactly. This lets you simulate the benefits of a really large effective batch size, but without needing the massive VRAM to hold all that data at once.
How does that work mechanically?
It's pretty neat. So normally, say you want an effective batch size of 64. Without GA, you'd load 64 examples, run the forward pass, calculate the gradient based on all 64, update the weights, boom, done.
Okay.
With GA, you might set your micro batch size much smaller, say 8. And then you set your gradient accumulation steps to maybe 8 as well.
So 8 times 8 is 64.
Right. What happens is you process the first micro batch of 8 examples, you calculate its gradient, but you don't update the model yet. You just store that gradient.
Okay, hold on to it.
Then you process the next micro batch of 8, calculate its gradient, and you add it, you accumulate it with the first one. You keep doing this for all 8 micro batches.
And only after you've processed all 8 micro batches, then you finally update the weights.
Exactly. You do one single weight update using the average gradient from all 64 examples. 8 micro batches, 8 accumulation steps.
Ah, okay. I like the analogy you used here too. It's like taking 8 slightly blurry photos sequentially.
Yeah, like your camera buffer can handle one blurry shot at a time easily.
And then you digitally average them together to create one sharp, clear image. You're averaging out the noise and the gradients from the small batches.
Precisely. You get the stability benefits of a large batch update, but you only ever needed the VRAM to hold one small micro batch at a time. Massive VRAM savings.
And that key formula people need to remember is effective batch, micro batch size, X gradient accumulation steps, X num devices. Super important not to confuse the micro batch size you set in the config with the much larger effective batch size the model actually trains with.
Absolutely crucial distinction. And the practical advice here is almost always start with a really small micro batch size, maybe even just one. Then you gradually increase the gradient accumulation steps until you see your GPU utilization get nice and high and your training loss curve looks smooth and stable.
It's the safest way to dial it in.
Definitely.
Okay, so let's say mixed precision and gradient accumulation still aren't enough. You're still hitting that VRAM ceiling. That's when you reach for lever 3, the memory lifeline, gradient checkpointing.
Right. This one is a more direct trade-off. You're sacrificing some computation time to gain back a significant chunk of VRAM.
How does it work? You mentioned the forward and backward pass.
Yeah, so remember, training has 2 main phases. The forward pass, where the model makes predictions and calculates intermediate values called activations. Then the backward pass, where it calculates the errors and figures out how to update the weights.
Okay.
The backward pass needs access to those activations calculated during the forward pass. And storing all of them, especially for models with long sequences or many layers, is incredibly memory intensive. That's often the main VRAM bottleneck.
Right, I've definitely run into that wall myself. So gradient checkpointing helps how?
Instead of saving every single activation from the forward pass, which could be tons of gigabytes,
Yeah.
it only saves activations at certain strategic points, certain check points in the network.
Okay. Not everything, just key points.
Exactly. Then, during the backward pass, if it needs an activation value that wasn't saved, it just quickly pauses, reruns the necessary segment of the forward pass on the fly to recompute that missing value, and then continues the backward pass.
So you're treading the memory cost of storing everything for the computation cost of rerunning parts of the forward pass when needed.
Precisely. And the payoff can be really substantial. You can often free up something like 30% to 60% of your VRAM. That can make a configuration that was previously impossible just suddenly runnable.
Wow, 30 to 60% is huge. What's the typical speed penalty for that?
It varies, but usually somewhere in the range of a 10% to maybe 40% slowdown in training speed. It depends on the model architecture and how often it needs to recompute.
Okay, let's use that photo editing analogy again. Standard training is like applying 100 filters to a photo and saving a full high-res preview after every single filter.
Right. Your RAM fills up super fast, but you can instantly jump back to any previous state.
Checkpointing is like saving maybe only after filter 1, filter 50, and filter 100, much less RAM used. But if you want to see what it looked like after filter 75,
The software has to replay filters 51 through 75 to reconstruct that intermediate state for you. Saves memory, costs time.
makes total sense. So the recommendation here seems pretty straightforward too.
Yeah, unless you are absolutely swimming in VRAM and raw speed is your only priority, it's generally a good idea to just enable gradient checkpointing. True by default. It's often the key to making things fit.
It's a powerful VRAM saver that doesn't actually change the final model math, unlike our next lever.
Exactly. Which brings us to the final and arguably most aggressive VRAM saving lever, the one you often turn to when everything else has failed to make the model fit. Quantization.
Okay, quantization. This is where we stop being subtle about precision, right?
Pretty much. The concept is simple. Represent the model's weights using fewer bits. Instead of the standard 32-bit or the mixed precision 16-bit.
To go lower.
We go down to 8-bit or even more aggressively, down to 4-bit formats.
And the impact on VRAM.
It's dramatic. 8-bit cuts the weight memory roughly in half again compared to 16-bit, and 4-bit cuts it in half again.
So you can potentially reduce the memory required for the weights by up to 75% compared to standard 16-bit training.
75%. That's obviously a massive game changer. It's how people are running huge models on, like, consumer GPUs sometimes.
It's absolutely essential for that. But there's a big flashing warning sign here.
The catch.
The catch. Aggressive quantization, especially going down to 4-bit, can definitely impact model quality.
How so?
You're fundamentally reducing the precision of the model's parameters. This can sometimes hurt its ability to perform complex reasoning, maintain coherence over long text, or capture subtle nuances in the data. You are trading precision for feasibility.
So it's not a free lunch.
Not at all. Which is why you rarely see pure 4-bit quantization used for the entire fine-tuning process on its own.
Right. It's almost always paired with LoRA, isn't it? Creating QLoRA. Exactly, QLoRA, or quantized LoRA. The idea there is clever. You load the massive base model weights in low-precision 4-bit to save VRAM, but the small LoRA adapter layers, the only parts that are actually being updated during fine-tuning, are kept at full 16-bit precision.
So the learning happens in high precision even though the base model is low precision.
Right. It helps mitigate some, though not necessarily all, of the quality degradation you might otherwise see from pure 4-bit training.
Okay, let's give people some concrete hardware context. Based on the source material, what kind of VRAM are we talking about for different model sizes, and when does quantization become necessary?
Okay, rough numbers. For a 7 billion parameter model, like a Llama 7B, you probably need around 16 gigabits of VRAM, maybe a bit more, for standard 16-bit fine-tuning. So quantization is often optional there.
Okay, what about bigger models?
Jump up to the 13 billion parameter class. Now you're probably looking at needing 24 GB plus of VRAM. On a common 24 GB card, using 8-bit quantization becomes highly recommended, maybe even necessary, to make it fit comfortably, especially with decent batch sizes.
And the really big ones, like 70 billion.
Yeah, for something like a Llama 70B, if you want to fine-tune in full 16-bit precision, you need serious hardware. We're talking 80 GB VRAM cards, like an A100 or H100.
Wow.
But if you only have access to, say, a 48 GB VRAM card, then 4-bit quantization, usually via QLoRA, becomes pretty much mandatory just to even load the model into memory, let alone fine-tune it.
Okay, so it really scales aggressively. You mentioned 4-bit, and the source specifically called out the NF4 format. What's special about NF4?
NF4 stands for normal float 4-bit. It's not just any generic 4-bit representation. It's a data type specifically designed by researchers to be information theoretically optimal for weights that follow a normal or Gaussian distribution, which neural network weights typically do.
So it preserves more information than a naive 4-bit format.
Essentially, yes. It leads to less quality degradation compared to simpler 4-bit quantization methods. It's generally the recommended 4-bit format to use for LLMs if you have to go that low.
Got it. So final recommendations on quantization. When to use 8-bit versus 4-bit?
Okay, so for a balanced default, if you need to save memory but want to minimize quality impact, 8-bit quantization is a really good starting point. Gives you roughly 2x VRAM savings for the weights compared to 16-bit, usually with very little noticeable drop in quality.
And 4-bit.
4-bit, specifically NF4 via QLoRA, is really for the fit-first scenarios. When you absolutely must get that larger model running on your limited hardware, use it when necessary. But, and this is important, if your fine-tuning task is critically dependent on, say, complex logical reasoning or generating highly coherent, nuanced text, try to avoid 4-bit if you have any alternative. Test carefully.
Because the quality hit might be unacceptable for those tabs.
It might be. You need to evaluate it for your specific use case.
All right, so we've covered our 4 big levers: mix precision, batch size and GA, gradient checkpointing, and quantization. Knowing they exist is step 1. Knowing how to actually use them strategically is the real skill. Let's talk workflow.
Yeah, the mindset here is crucial. Optimization should feel like careful navigation, not like brute force. You want to start with a simple, known, stable configuration.
Like maybe just BF16, true and micro batch size, 1.
Exactly, a very basic starting point. And then, crucially, only change one parameter at a time. Observe the effect. Did it speed up? Did it use less memory? Did it crash?
Right, avoid the temptation to tweak 5 things at once.
Because then if it breaks, you have no idea which change caused the problem. You're basically building a personal map of how these levers interact on your specific hardware with your specific model.
That makes sense. Prevents a lot of frustration. So what's the recommended sequence? If someone's starting out, what's the crawl, walk, run approach?
Okay, step 1. Crawling, get stable, start with mixed precision, set BF16, true, or FP16 if you absolutely have to, but BF16 is preferred. That has memory right away and speeds things up.
Okay, foundation laid. Step 2, walking. Now manage throughput. Set micro batch size low, probably 1 to start. Then, you carefully increase gradient accumulation steps. Watch your GPU utilization, you want it high. Watch your loss curve, you want it smooth. Tune accumulation until you hit that sweet spot.
Step 3, running low on fuel. If, after tuning batch size and GA, you're still running out of VRAM, then you pull the memory lifeline. Enable gradient checkpointing. True, accept the small speed hit to gain back that big chunk of memory.
And quantization is always dead last.
Always. Step 4, the last resort. Only after you have a stable working configuration without quantization should you even consider it. Start with 8-bit if needed. Only go to 4-bit NF4 if absolutely necessary to make it fit.
Why last?
Because you need a baseline. You need to know what level of quality your model could achieve before you start potentially degrading it with aggressive quantization. Otherwise, if the final quality is bad, you won't know if it was the quantization, the data, the hyperparameters.
Isolate the variables. That makes perfect sense. And it highlights a couple of common pitfalls people run into, right?
Definitely. The biggest one, probably, is confusing microbatch size with the effective batch size. They set microbatch to 1, accumulation to 64, and then think their batch size is 1, so they crank up the learning rate and everything explodes.
When really their effective batch size is huge.
Exactly. The other big mistake is jumping straight to 4-bit QLoRA without ever running a non-quantized version first. They get mediocre results and blame the model or the data when maybe it was just the 4-bit precision loss all along.
So mastering this interplay precision, batching, checkpointing, quantization, and knowing the order to apply them based on your constraints, that's the core skill for stability.
That's the art and science of it, yeah.
So you've given everyone the toolkit, the levers, and the strategy. The real skill now is for you, the listener, to take this and adapt it, build that personal map for your hardware, your models, your goals.
Absolutely. And maybe just as a final thought to leave you with, now that you've gotten a taste of the complexities, the VRAM juggling, the calibration needed just to get fine-tuning stable, let alone optimal, it raises a bigger strategic question. With these massive foundation models getting better and better all the time, seemingly week by week, is the long-term value of building, owning, and constantly maintaining your own custom fine-tuned model always going to outweigh the cost and effort involved? Or, for many tasks, might relying on the ever-improving general-purpose foundation models actually be the smarter long-term play?
That's a really interesting point, the build versus buy dilemma, but for fine-tuning.
Exactly. Something to mull over as you navigate the optimization landscape yourself.